Jambo Nangadev, hello. This is Dr. Marcelini Dabo talking to you. I am a PhD on control systems. If you wanna check my PhD thesis, I invite you to follow this link. I am also a consultant engineer in industry, an independent researcher. And then if you wanna reach out about the different subjects I have treated, please send your email at contact@daboacademy.com. So thank you very much. So I have been presented second order systems and also first order dynamical systems, both of them, through different videos with my scientific innovations and also with my vision, new vision about these dynamical systems. Um, so don't forget that I have introduced an important result for second order dynamical systems. That is, any given dynamical system of second order has in reality only one time constant. And this result is very powerful and it is changing the way modern control engineering is seeing designs or characteristics of second order dynamical systems. So today I am happy to talk to you about second order dynamical systems in terms of ordinary differential equations with an application that is a RLC serial circuit, meaning that R stands for the resistance, L for the inductance, C for the capacitance, and then both are linked in a serial way. And this circuit is used in electronics and helps to do many applications like filtering of signals, for example, and other stuffs. Okay, so before we go further in this presentation, just to remind you that my book is coming very soon, and please be aware and be ready to order yours because this will bring to you excellent information and also many innovations that I have introduced that will be very helpful for you. Okay, so now let's consider this RLC circuit. So you can see that this is the power supply. It is a continuous current power supply here, named U of t, and then this will produce voltage, okay, upon our RLC serial circuit, and a current that will go through all the components, through the resistance, the inductance, and the capacitance, and then will come again by the negative entrance here. What we can say about this, we want to do the modeling of this electronic system. So to use this, we use the second order Kirchhoff laws, which can be written like the sum of the voltage for the sum of the voltage for different components that you have here, that is equal to the voltage to the power supply voltage. Okay, this is what you have here, where U R is R times I of t, the I that is a current that is going through all the components that you have here. For the inductance, it is written L multiplied by the derivative of the current according to time, to which you add the component, the voltage component for the capacitor. And all this sum is equal to U of t, that is the input voltage. So for the capacitor, the current is given as C derivative of the capacitor voltage divided by T, okay, according to time. And all this expression is a function of time, of course. And then if you replace the I and replace also the derivative of I in this expression that you have here, So by doing so, you will have this last equation that is a pure second order dynamical system, as you can see it here. So where you have here the static gain, which is equal to 1 here. You have the coefficient A1 over A0, which is equal to RC, and the corresponding LC that is equal to A2 over A0. So reconsidering the previous expressions that I have explained on the previous videos, we consider that this tau and this tau is the time constant of the surface of time. Okay, I have explained this in previous videos. This is a natural time constant, okay, that you have. And as said previously, the static gain for this equation is equal to 1, okay? And then if you consider also this expression, this way of writing second order systems, you will have an identification term by term. So with these expressions, tau and this tau equal 1 over omega n squared, that is equal to L times the C, and tau and this n, the natural time constant, is equal to 2c divided by omega n, this is equal to RC. If you make the ratio between tau tau, the time constant of the surface of time divided by the natural time constant, I'd have defined what I have called the relative time constant that is equal to the to 1 divided by 2c omega n that is equal to L over R. Remember that this L over R for just for a RL circuit, serial circuit, it is the time constant of this RL serial circuit, okay? And finally, the gain the static gain of such a circuit is equal to 1 over R, okay? So if you consider this time constant, this relative time constant, if you want to have the time constant of your system in the sense of Dabo, meaning that in the sense of my definition and my scientific innovation, you just double this expression and this will give you this time constant, this unique time constant in the sense of my definition for a second order dynamical system like an RLC serial circuit, and it is equal to 2 multiplied by L over R. So you can see that the second order dynamical system has double of the time constant for a RL circuit, okay? Second order dynamical system in terms of application for a RLC serial circuit. So this is very important. So now from here, what are we going to do? I'm going to show you how you go through the applications. Okay. So we have done our modelization. We have defined the time constant of our system, of our RLC serial circuit. We have these two expressions here that we will be exploring, meaning that 1 over omega n squared equal L times C and 2c over omega n equal RC. And from here, we deduce these expressions that are resumed in this table with this expression that is the relationship between the natural pulsation, the time response, and the natural frequency of our dynamical system. For this expression, it comes from the tables that I have introduced. I will show you in the next picture the details. So here, for time responses or rise times, what you have is always a constant that I have written here by capital A of Xi, so it can be written capital A of Xi, and also gamma, where gamma is a percentage of the output according to related to the equilibrium point. Okay, and then this is a constant. This I call them constant of Dabo. meaning myself, because it is part of the constants that I have introduced. So if you take this, the time response at a given constant, for example, gamma equals 95% of the equilibrium, you will have time response of at 95% is equal to capital A of xi divided by omega n here. Of course, omega n equals 2 times pi times Fn, that is a natural frequency, okay? And then this is a design, this is a table of design where you can design your system. If you fix, for example, your resistance, you can design your system according to reach some temporal performances by computing the corresponding inductance that will allow you to reach that performances, and also by computing the capacitance to reach also same requirements or same temporal performances. So now let's fix the resistor of our system in this example, for example. For instance, we fix the resistance. And then we say for our system, we don't want to have an overshoot. So at that moment, we fix the damping ratio, because if you don't want to have an overshoot, you should choose a damping ratio that is equal or greater than 1. Once it is done, so if you fix the damping ratio, you come here, you fix the desired time that you want to have. We want to have a time response at 95% of the equilibrium. Let's say that is equal to 1 millisecond or 100 millisecond or 2 microseconds, etc. And then according to the gamma that you have fixed and also the damping ratio, you will choose the proper constant, Dabo constant here, that is capital A of x, of xi. And then with these values, you will be able to compute the inductance and then derive compute also the capacitance, okay? That both will give you, such that both will give you, of course, the time response at a fixed percentage with or without an overshoot. Okay, so how to make the design of your RLC circuit? You just, as I was saying, fix the damping. You first fix, okay, the desired damping ratio. And then if you want temporal performances, what you do, you fix the percentage of the equilibrium, that is gamma, that you want to fix. And then at this value, which percentage do you want to have and which value of t that you want to have. So you fix first the xi, you fix after the percentage and the value that is equal to the time. And thanks to this xi and gamma, you will be able to choose your corresponding A from Dabo tables, meaning from the tables that I have introduced. So by doing so, as you have fixed it the R, you can compute the inductance. You will be able also to compute the capacitance, okay, of the system. And then for this, you will be having all the your complete elements, okay, your complete parameters in terms of resistance, inductance, and capacitance, okay? And then if you want also to have a frequency-based performances, what you do is that you choose your frequency, natural frequencies that you need, for example, 1 kilohertz or 2 kilohertz or 3 kilohertz, etc. You say to yourself, okay, I don't want an overshoot, or I want an overshoot, so you fix xc. As previously you have fixed your R, what you do, you compute your L and you compute also your C. This is in terms of frequency-based performances that you want to respect according to your specifications. If you have fixed the xi and then you have chosen your Fn, you can see that by choosing Fn, you can derive the omega n, and then because you will just consider that omega n equals Fn times 2 pi, and then, or you just multiply, okay, this one, and from this, as you know, xi, you take out the consequence of this time response by choosing the correct A of Xi in the right table. Okay? So going from here, if you check this video and there are some points that are not clear, please contact me and I will be happy to explain you or give you another details for the examples. Right, so now let's go. So going from here, let me just show you the next with an example. So I recall the same table here. And then from here, what we have, these are some tables, some parts of tables that are present in my book, where I give the resume of all these formulas. And if you purchase this book, of course, you will be able to see all the details of these different damping ratios that you have here and the related formulas that you have here. Okay, so this is the table for a damping ratio that is equal to 1, and it is divided in two parts where you have at the left here you have rise time, okay? And then on the right part here you have time responses, and time response at 95%, for example, knowing the omega n, to compute it, it is equal to this expression. This is how you read this table. The time response at 90%, it is equal to this expression, and same for this, and also same for this part of the table. And then from here, what you do, if you desire, for example, a given time response that is here, okay, this time response that you fix, for example, at 1 milliseconds, what millisecond is equal to 4.742, okay, and then if you know this, which omega n will you be taking? You derive your omega n. This is how it works. And the omega n, this is because previously what we had is the omega n is equal to this expression. So here is A, capital A of Xi. That corresponds to the 95% and Xi equals 1. And it is the same thing for the other percentages here, as you can see, and always for the same Xi, okay, for the same Xi that is equal to 1. This is a table of it. Okay. So now let's go for this table now, where you have the Xi here that takes different values, 0.5, 0.7, 1.25, 1.8, and all of them you read the values vertically, where you can see that the overshoot here for 0.5 is 16.3%, and for 0.7 it is 4.6%. Of course, you don't have here an overshoot because you have a system that is overdamped. And then the expressions I was telling you, omega n times t, is the same expression that you have here, okay? You have your omega n times t equal capital A of Xi, okay? This is exactly what you have here, okay? The omega n is times the time response is equal to the capital A of Xi that is here according to the given percentage, according to the Xi also, and that is what you have also on the rest of the table. Same thing for the omega n times the time response at 19% of the equilibrium, 90% of the equilibrium, and for 80% of the equilibrium, you can see different values of the coefficient capital A of Xi and of the percentage of the equilibrium, that is gamma. So from here, let's now go for some simulations. I will take specific examples, okay, to show you how you will be deriving this. And of course, don't forget the book that is coming very soon. So for to start, we consider, okay, we consider the list of damping ratios here from 0.5 and the different values that I have listed and presented on the previous table that you have. And then you see here the time response at 95%. I fix it at 500 microseconds. And these are the coefficients that you have, the corresponding coefficients that you have here, for example, for the first line, for the second line, that corresponds at 90%. For the third line, that corresponds also at this third expression that you have here. Okay? And then the capacitor that you have here is written here. Okay, so I fix the capacitor for this example, and then for the capacitor, I compute the resistor according to these formulas that I have here. So I just derive here the R, okay, and then compute the C. Here I derive the inductance, and here I take the frequency. This is the omega n corresponding the time response and the second time response. And by computing this, I have all these results that you can see here, okay, in the command window. And then from there, I will be moving to LT-SPICE environment to show you that for the simulations, I will have always the same time response that I have specified at the beginning at 95%. Whatever can be the damping ratio at the beginning. Okay? So let's go. And here how you read the results. This first result for the resistor, you read them vertically for all of parameters. For example, if I consider the damping ratio of 0.5, it is equal to this damping ratio in order to have a time response at 95% that is equal to 500 microseconds, I should take a combination of this resistance, 2.2 kilowatts, kilo ohm, sorry, this inductance, and then the corresponding frequencies that I will be having will be this one, of course, exponent 3, and then the omega n, corresponding omega n is here, and the time responses that I am supposed to have at 90% of the equilibrium is given here, and at 80% of the equilibrium is also given here. So this is what I am supposed to have. So I know the time responses before I compute them. Okay, this as a consequence, it's very important. I have fixed this time response. I fixed also the damping ratio. And then from both, I can compute in advance the time response that I will be having as a consequence of these choices. Okay, so now let's go for the simulation with this software that is LT-SPICE. So from there, you can see that just because I have done previous simulation, so I will not restart. Look at this, it is the last value of the resistance, the last value of the inductance, and the capacitance, that is 0.1 microfarad. And then I am supposed, so the values of resistance is here. Don't forget it is to the power 10 to the power 3 multiplied by 1000 here. This is why you have it here. Okay. And then the inductance is here, 24.1 milli. It is here. Okay. And then the capacitor is here. It doesn't change. Okay. Capacitor is here, 0.1 microfarad. Okay. And then from there, this is what we have. For the computation, we are supposed to have 500. So I can resimulate. And even if I resimulate, you can see that, for example, here, Okay, we have always at 95% because here we have millivolts, and then as we have 1 volt here, it is 950 divided by 1000 volts or 1000 millivolt, and this gives us 95%. As expected, we have the corresponding time that is 500 microseconds. If we position ourselves at around 80%, we have the time response that is equal to 276.3 microseconds, as you can see it where you can see it here. Okay, don't forget that if you take this 276, you multiply by 1000, so to have it, you will have again 1 exponent minus 3, like this one, it will be 1 exponent minus 6, that is the microseconds. Sorry for my voice. And then, sorry. And then here, this is exactly what we have. So if we go from this value, and then we choose another one, that is, let's say, this value will corresponds to 1 point. Let's just 1.25, okay? And then if you consider that what 1.25, so if I want to simulate that, I will consider, let me check again how much it will be, 1908.4. 1908.4, this is the resistance that we have, and the corresponding inductance is equal to 58.3 milli. So 58.3 millihenry. And then going from here, I reproduce exactly the given values here. 908.4. And then here, I say 58.3 milli. Okay, so if I do this, if I simulate, I will not have an overshoot here. You see that here, this is always at 95%, let's say, and this is always the 500 microseconds that I am supposed to have. Here, it moves a bit, but if I want to have the given value at 80, I will just position myself here and bring it to 80, and the corresponding value should be 289. At 80%, if I check here, the 80% response time, 289 microseconds. Okay, so this is what I have expected, and if I want to check the corresponding frequency, it should be at 2.08 kilohertz. If I simulate this, so I just position myself at 90%. Okay, this is what I call 90% minus 90% for second order systems, and the corresponding frequency is here 2.1 kilohertz as computed here around 2.11 kilohertz before, thanks to my formulas, so thanks to the scientific innovation I have introduced. Okay, so from here now let's take just one point. If I take the case for which I have 0.5, it corresponds to this value of resistor, this value of inductance, and the capacitance will not move. So 2208.5. Let's put it here. 2208.5. This is what we have. And then from here, we have 487.7. So 487.7. Let's go for it. Okay, so this one, I just delete it. And then here I say 487.7 millihenry. This is what I have, okay, as an inductance. And this inductance By simulating this, because the capacitance is always the same, I will have an overshoot here because it's a value corresponding to a damping ratio less than 1, that is 0.5 in this example. And then let's go to simulation. You see the overshoot here. The 95% that we have is always here. Here we have the 500 microseconds of response, and then we are supposed to go here until 800. So let's go to 800. So 802, let me just zoom and try to find precisely the points that I am looking for. Here. Okay, just do it like this. So I have something correct. And then from here, the time response that I am supposed to have at 80% of the equilibrium, that is 1 here, is equal to this value, 416.3 or zero point 0.2 or zero point 0.4. If we check here the time response at 80%, we can see that the good value is here. Okay, and then I even can check the value at 90% and see that it will be this one. Let's go for it. We say 90%. 90% will be up. Just let me de-zoom and then zoom again to, yes. Okay, so if I go this way, okay, let's say that we reach it, and then the value is 469.6. If we look at here, 469.5, you see? So it is quite the same value that we have computed. So this is a way that you can design, okay, a dynamical system, an RLC serial circuits, okay? And then this will help you to understand the time response that you have here. That is your time response. And here, if I want to check the corresponding frequencies that I have, I just check the same, put the same values here, okay, for resistance and inductance. And I will see here, if I position myself at minus 90%, because for second order on the board diagram, you go from zero, around zero, okay, decibel, and then you move in terms of angle, I want to say, not for the decibel. So you can see that the zero angle is here up to 180, okay, degrees minus 180 degrees. And then at the middle, it corresponds normally to the natural frequency, okay, here at minus 90 degrees around. This is how I check the frequency that I am supposed to have in this case. And then now, when you do this, you see that the values that you are waiting for are here. Okay, excuse me here. This is your specification, and this is the consequences of your specification. So you can see that these uh, results that you have here, for example, for time response at 80%, or let's take for this one time response at 90%. If you want, for example, to have the time response at 95%, that is equal to the fixed value, that is 500 microseconds. And then you want a time response at 90%, that is less than this value. So you should take the damping ratio that is greater than 0.6, because you can see that the tendencies is decrescendo. It is decreasing, okay? You see that the time response is decreasing here, okay? And the more the damping ratio is big, the less you have a time response at this 90%, okay? And then, of course, if you want a greater time response, just reduce this value, put it at 0.4, etc. And, of course, you will be using the Dabo formulas. You can also, as I told you, fix the frequency, the natural frequency of your dynamic system that you want to have, and this will be a consequence in terms of time, and then I let you do that exercise. You come back here, for example, and then you fix the frequency because the capacitance is fixed. Okay, if you fix the damping ratio and you fix the frequency, you will derive the resistance. If you derive your resistance, you will be able to compute with the fixed values your inductance, and then from there you will have all your three elements. Okay, and then if you do that, you come here, you have your omega n. Once you have your omega n, as you have chosen your xi and your percentage, you can compute your percentage here, the time response, sorry, at a given corresponding percentage by fixing this percentage first, for example, saying that as I know that now the frequency, I want to derive the time response corresponding at 95%. And how much it will be? It will be time response equal at 95%, the corresponding value of capital A of xi divided by 2 pi multiplied by the fixed values that you have chosen as the frequency. Thank you very much for your attention. And so you can see that in this presentation, I have used the two software for computation, that is the MATLAB and then also the LT-SPICE. And both can be, of course, you can do things between them. So again, thank you. I hope that your Christmas was a Merry Christmas. And then I wish you a Merry Christmas. And then I wish you also to have good time and to enjoy your life and to do everything that you love to do. I wish that for you. And I say to you, Happy New Year also, if I don't do some videos in between. And may this new year that is coming bring to us good health, good opportunities, and also nice way of doing things. So please share this video, like it, subscribe to my channel to support what I'm doing, and also share. Thank you very, very, very much, and I hope you have enjoyed. Bye.